In this video, we're going to take a look at a couple more examples of exponential problems. One where we don't even know the exponential growth rate or the original amount, and we have to do some solving, and another one where we have to do a little bit of finagling because we can't solve algebraically. All right, so let's start with the first one. For a population that demonstrates exponential growth, meaning a consistent percent of change, we know the following. P sub 3 is 12.675 and P sub 4 is 29.1525. Well, we need to figure out what the common ratio is, and then we can work backwards a little bit and figure out what the P sub 0 is. Okay, so the common ratio is going to be the ratio between P sub n and P sub n minus 1, between one term and the one right before it. So I take the 29.1525 and divide it by the 12.675 and come up with 2.3. So that's my common ratio. So how do I find the initial population? I recall my basic formula that says P sub n is equal to P sub 0, the initial population, times that 1 plus r raised to the n, and that 1 plus r altogether is the common ratio, or the growth multiplier we've also called it. So we know what that parenthetical statement is, and we know for P sub 3, the answer, P sub n, should be 12.675. So I can go ahead and take on the right-hand side 2.3 cubed times itself 3 times and come up with 12.167. And then to find P sub 0, we would go ahead and divide and get our final answer of initial population of 1.04175. So we're using the same formula we've used before, the explicit formula for exponential growth. We're just plugging in different information and solving for different things. All right, here's another one that's a little bit different. It says Portland's population in 2007 was about 568,000, and it has been growing by about 1.1% per year. Writing a recursive formula. All right, well, we're going to start with the initial P sub 0, 568, and I'm not going to put the zeros. We're just going to assume our answer is in thousands. So P sub 0 is 568. Then P sub n is the percentage that we're changing, 0.011 times P sub n minus 1. Okay, so we just take the rate times the term right before. What about the explicit form? Well, the explicit form requires that we put in the initial amount, 568, and multiply it times 1 plus the rate of change, so 1.011 raised to the n power. So it's similar, but we have to add that 1 in there to show that we've added the previous term in. Okay, here's the tougher question. If the trend continues, what will Portland's population be in 2016? Okay, so what I have to stop and think about is, how is 2016 related to this problem? My model started in 2007. So that represents year 0 or time 0. So I have to figure out, where is 2016 in relation to 2007? Well, it's a little subtraction problem, and we get n equals 9. So we want to really find P sub 9. So we put in the exponent of 9 on our growth multiplier and work it out and come up with about 627,000. Okay, let's complicate it a little bit further. If the trend continues, when will Portland's population reach 700,000? Well, now what we've been given is the P sub n value, and what we don't know is the exponent we're supposed to put on there. The reason this is a little tricky is because I can't solve this just by simply dividing. When I have an exponent, I can't divide away the base. That doesn't help me. That doesn't undo exponents. So what are we going to do? Well, one option we have is graphing. Okay, so what I've done here is I have put together a graph of our particular situation where we have the years since 2007 is my X coordinate. Population is my y coordinate. It's in thousands. And then I've plotted that out and got a model here. And so if I look, it looks like, okay, here would be about, if I look for 700, it looks like right here is about where it would cross the line, intersect my model. And if I drop down, that looks like at about year 18. After 2007, so I'd have to say 2007 plus 18, 2025. Okay, that's a little bit challenging. It's not very precise. It's an estimate, but in another video, the next video, we're going to take a look at how could we algebraically solve this. It's actually going to require something called logarithms. So check out that other video to find out how we can do this more precisely.